Magnetic force. Remember the pattern. There's some kind of a source, and for a magnetic field, the source is a moving charge, a single moving charged particle or a current, either one, or a magnet, and that source creates a field, a magnetic field, and then when something else comes into the region of space that has that magnetic field, and specifically it's some other moving charge, then that new thing that came into that region of space feels a magnetic force. And the rules for magnetic force are considerably more complicated than the rules for electric force. Here's the rule for magnitude of a magnetic force. It's proportional to the strength of the magnetic field, that makes sense, and it's proportional to the amount of charge that the moving object has. But it's also proportional to the magnitude of the velocity. It's proportional to the speed, because the charged object has to be moving in order to feel a magnetic force. So this term has to be non-zero. And then there's one other weird factor here, sine of an angle. We had nothing like that in the rule for electric force. The angle specifically is the angle between the magnetic field and the velocity. So all that, more complicated rule for magnitude, and the rule for direction is rather unusual. Remember, in the case of the electric field, the electric force on a positively charged particle simply pointed the same way as the electric field, and the electric force on a negatively charged particle just pointed in the opposite direction. That's all there was to it. Here, the magnetic force points, one thing that's strange about this, the magnetic force always comes out perpendicular to the magnetic field and perpendicular to the velocity. That is, a line like this representing a magnetic field line, and then a second line defines a plane. You can define a plane by just two lines. And so in this case, that's the plane of the blackboard. And then in this case, the magnetic force on a charged particle will be perpendicular to this, either pointing out of the blackboard or pointing into the blackboard. Okay, the rule for finding the direction of magnetic field is complicated enough that we have a little procedure for it. We call that procedure another right-hand rule, and there's several parts to this right-hand rule. It's all spelled out in a nice highlighted box in the text in chapter 24. But let's look at some examples. So remember, we had this rule last time for finding the direction of a field caused by a long straight wire. We started by pointing our thumb in direction of the current. This time, we do something similar for start. We take our thumb and point it in the direction of motion for the charged particle, the direction of velocity. So, thumb in the direction of velocity. And then take your index finger and point that in the direction of the field. And to do this right, you're going to have to sometimes just twist your arm around a little bit, maybe stand in a different orientation, turn the paper over. If you don't do that, if you aren't doing that kind of thing, you will get it wrong sometimes. You gotta, if you just stop and think about each step and don't go on to the next step until you are sure you've got the previous step right, then things will go okay. So, thumb in direction of the velocity, field in, or index finger in direction of the field. So now I've got my thumb pointing up this way and index finger in direction of the field. Then take your other three fingers and rotate them so that they're now perpendicular to the thumb and the index finger. In other words, perpendicular to the direction of the velocity and perpendicular to the direction of the field. Index finger points in the direction of the field, and then the other three fingers, rotate them, keep them straight this time, don't curl them, rotate them so until they are perpendicular to thumb and index finger. And once you do that, now you have the direction of the force. And specifically, it's the direction of the force on a positive charge. And just like in the case of electric force, if you have a negative charge, the force points the opposite way. So that's the direction of the force on a positive charge. So looking at this example, thumb in direction of the velocity, that's the first step. Index finger in direction of the field, that's the second step. Curl your fingers, or twist your finger, other three fingers, until they are perpendicular to thumb and index finger, in other words, perpendicular to velocity and field. And when I do that, the fingers now point this way into the blackboard. So that is the direction of the force on a positively charged particle. And the opposite direction will be the direction of the force on a negatively charged particle. So for example, if we have a positively charged particle that starts moving this way, but then as soon as it feels the magnetic force, it feels a force pushing it this way, so it's going to still move up and to the right, but now it's feeling a force this direction, so its path will now be curved. It'll start moving that way. Let's look at another example here. So magnetic field, let's say, points this way, and the velocity points this way. And let's say this time we know what the charge is and it's negative. So follow the rules. First, thumb in direction of the velocity, index finger in direction of the field, and then fingers, curl those fingers again until they're perpendicular to index finger and thumb, and then again they point in that way, so that, the three other fingers, gives you the direction of the force on a positive charge that way, but since this is a negative charge, the force points the opposite way, points perpendicular to the blackboard, out of the blackboard. All right, so one more example. Let's take a look at a magnetic force that a cosmic ray particle might feel from the Earth's magnetic field. So here's the Earth and the North Pole and South Pole, or rather North Geographic and South Geographic Pole. The Earth acts like a big magnet. And so there's a magnetic field, and the shape of the magnetic field lines goes like this. And that is, field lines all radiate away from some point here in Antarctica, and then they all head for some point here up in the Northwest Territories of Canada. But I remember, as you saw in section 2 of chapter 24, whenever you're talking about some magnetic object, it's got a north magnetic pole and a south magnetic pole, and those two poles are defined so that field lines always come from a north pole and head toward a south pole. So actually, the north magnetic pole is down here in the geographic south, and the south magnetic pole is up here in the geographic north. But for our purposes, here at mid-latitudes and tropical latitudes, the electric field lines basically point north and basically are parallel to the surface of the Earth. So let's say we've got a positively charged cosmic ray particle, and then so the velocity of the cosmic ray is headed this way. And what kind of magnetic force does it feel? Well, same rules, thumb in direction of the velocity, index finger in direction of the field, right at these latitudes where the particle is aimed at. Field pretty much points north and perpendicular to the surface. So here's the direction of the field at those latitudes, and here's the direction of the velocity. Then curl your fingers again, same kind of result as we've seen in the other examples. Curl my fingers. Sorry, I shouldn't say that. Rotate the fingers, don't curl them. You want to keep them straight. So now there's the direction of velocity, there's the direction of field, there's the direction of the force on a positive particle like this cosmic ray. Pointing that way, parallel to the plane of the blackboard, pointing that way. In other words, as the cosmic ray particle heads toward the Earth, it's feeling a force this way, so that means its path will be deflected that way, deflected towards the east. one other kind of situation here, a little bit different. Let's say we don't have to figure out the direction of the velocity. Let's say we know it, but let's say we know the direction of the force, and we know the direction of the velocity, and we know the direction of the field. The one thing we don't know is the sign of the charged particle that is feeling that force. But we can figure that out if we know those other three things. So let's say there's a velocity like this that is perpendicular to the blackboard pointing out, and then magnetic field in the plane of the blackboard pointing left to right, and then the magnetic force that you get is that way. That is, the particle is moving this way at first, but it feels a force like this, which will deflect it upward. It'll still keep moving away from the blackboard, but then it'll also gain an upward component to its velocity. So a particle that is moving like this and feels a field like this and feels a force like this, is it a positive charge or a negative charge? Well, let's just go through the right-hand rule again. Thumb in direction of the velocity, index finger in direction of the field, points to the right. Turn the other three fingers so that they're perpendicular to those, and then we get a force pointing up. Remember, when you're doing this rule, this right-hand rule, the way your fingers point is the direction of the force on a positive charge, and that's the direction of the actual force in this particular case. So the thing that is feeling this field and feeling this force must have been a positive charge. One more example. Let's turn that velocity around. Say it's still perpendicular to the blackboard, but now pointing into the blackboard, pointing away from us. And we'll rotate the direction of the magnetic field. So now it's pointing straight down. And the direction of the force we get from that is that way, straight to the right. Okay. Again, use the right-hand rule, see what kind of a direction we get for this. This will tell us the direction of the force on a positive charge, and then we'll see if this direction is the same or opposite to the direction of the actual force. So again, thumb in direction of the velocity, index finger in direction of the field. So now I'm like this. Index finger points down for the field direction. Thumb points into the blackboard for the velocity direction, and I rotate the fingers so they're perpendicular to thumb and index finger. And now those fingers point to the left. So that is the direction to the left of force on a positive charge. But the force is actually going to the right, so it must be a negative charge that's feeling this kind of force. If it were a positive charge, it would feel a force pushing it to the left instead of the right, because to the left is how my fingers point when I do the right-hand rule. Okay, you can have a magnetic force act on not just one charged object. You can have a magnetic force acting on a whole bunch of charged objects all at once. like a current. Well, let's look at a situation like this where we have two currents. Call it current A and current B. And they're parallel to each other. They're both perpendicular to the blackboard, and both currents are pointing out of the blackboard. This is going to feel a magnetic force, and this is going to feel a magnetic force. This feels a magnetic force because these are moving charges, and they're moving through a space that has a magnetic field. And this space has a magnetic field because of this other current. Current is a source of magnetic field. This current is the source of a magnetic field that is felt by this current. And since this current is moving charges feeling a magnetic field, it'll feel a magnetic force. And similarly, this current is the source of a magnetic field over here that is felt by this current, and this current is moving charge, feeling a magnetic field, so it will experience a force. First, let's look at the force on A. Same rule, start by pointing your thumb in the direction of the velocity of the moving charges. Remember, whenever we use the symbol I, we're talking about a conventional current, which means we're imagining that the moving charges are positive charges. And in this case, they're moving this way, so that's the direction of my thumb. Well, and then I want to find the direction of the field that this thing feels. The field that this thing feels has this other current as its source. So what I want to know is what's the direction of, at these points right around here where current A is, what's the direction of the magnetic field that was caused by the other current? This is a straight wire. So we know that the field lines are concentric circles centered on that wire. And so you can imagine a field line passing through that point where current A is. And that point there would be, these are in the same plane, and this is the center of all those circular field lines. Then this is the leftmost point on one of those circular field lines. So the direction of the field right here at the left edge of the circle is along a line that's tangent to the circle at that point, and at that point the tangent is vertical. So the field here, the field that's caused by current B, and the field that is felt by current A is pointing either up or down. Which one is it? We go back to the right-hand rule that we thought about the other time that gives us direction of field. Thumb in the direction of the current. Now curl your fingers, and that shows the flow of the circular field lines. For this current, the circular field lines are flowing counterclockwise. So at this point, the field lines flowing counterclockwise, meaning at this point, the field is pointing down, not up. That's the field caused by current B. Now we can find the force on A. Thumb in direction of the motion of the charged objects. Index finger in direction of the velocity, and then rotate your fingers so that they're perpendicular to thumb and index finger. And when you do that, those three fingers point left to right. That's the direction of the force on a positive charge, and we're imagining that this is conventional current, so we're imagining that this is positive charge. So the force that it feels is to the right. In other words, it's an attracting force. This one is being pulled towards B by the field that B created. Now what about the force on B? To do that, we need to know what the magnetic field over here is like. And the magnetic field over here is the magnetic field caused by the other current. And again, remember that field caused by this current has field lines that are concentric circles centered on this. So the field line that this point is on is a point on one of those circles. And since they're in the same plane and this is the center of these circles, then this is the rightmost edge of one of the circular field lines caused by this current. And so we know here that the field at this point then is along a straight line tangent to the curved field line, so it again points either up or down. And which way, we figure that out with the thumb field right-hand rule. Thumb in direction of the current, curl your fingers and they show the flow of the field lines, again, counterclockwise. So the field lines around A circulate counterclockwise. So at the location of current B, the field from A is pointing up. There's the field from A. Now we can figure out the force on current B. The movement of the positively charged particles that make up current B is this way, so that's the way I point my thumb out of the blackboard. Up is the direction of the field that B feels, so that's how I point my index finger. Turn the other three fingers so that they're perpendicular, and that gives me the direction of the force on positive charges. This is conventional current, so they are positive charges. So right to left is the direction of the force on B. In other words, for these two parallel currents, each of them is applying an attracting force to the other. This one is being pulled towards B, and this one is being pulled towards A. Okay, this is all a little strange. It takes a little bit of getting used to. And so the assignment that comes after this is just some exercises with the same type of thinking as I demonstrated here.